back to the dark side. So we're going to talk about search today and mostly about depth first search. I'll allude a little bit about what we need to do next, but mostly this video is about depth first search. We'll talk about state management, which is a big issue in the subsequent video. All right, let's talk about depth first search. So what I need to make you understand is how the search works in MiniCP. And so we are exploring a search tree. You know that in a search tree, you have nodes and then you have subnodes and so on. Now the nodes in MiniCP represent subproblems to be solved, right? So you have an initial problem and then you could decompose it into subproblems when you get stuck propagating and filtering the domains. So essentially every node represents a subproblem to solve, okay? And what we do in MiniCP is that we are developing branches. Branches are essentially taking one of these subproblems and splitting it into, smaller subproblems. And these smaller subproblems must partition the search space, and they will typically act on variable. Okay, and once again, what you're going to see that in the MiniCP system, the only thing that we will be doing is specifying this branching scheme, the way you generate these branches. All right, so this is the search space, the branches, and the node for the queen's problem. So this is the root. All the variables take the value between 0 and 7. This is the 8 queens problem. Okay, now. At some point here, you have to start branching. And so the branching scheme here is going to create two constraints. The first one is going to be Q0 equals 0, and the other one on the right side is going to be Q0 not equal to 0. Now, once you implement this particular, when you add this constraint to the system, it's going to prune the search space. So you see the search space which has been pruned here. The second queen here cannot take the value 0 and 1. The third one, cannot take the value 0 and 2, and so on and so forth, right? And so this is what's going to happen inside the system, the constraint propagation. So in this particular node, you have a description of the search space. Same thing here, except that here is very simple. The only thing that I have done is removing one value from the first variable. Now this node, again, you're going to propagate, but then afterwards you have to split again. And here you see that you are adding the constraint Q1 is equal to 2, and there the constraint Q1 is not equal to 2. And once again, you're going to propagate, get this search space, get that search space. Isn't this a very, very cute slide? I love it. So now we have to implement something like this, right? So what you see is that the branching decision, the branching that that you apply at every one of the nodes is actually partitioning the problem, very often around a variable. But even if you select a variable, there are many different things that you can do. You can assign a specific value or make sure that the variable doesn't take that specific value, or you can say that the variable has to take its minimum value or not its minimal value, or you can do domain splitting like we have seen in the magic square problem. So there are many ways of actually implementing these branching schemes. But the key point is that they have to partition the search space, okay? Now let me formalize this a little bit. If you have a constraint satisfaction problem, X, D, and C, where X are the set of variables, D the set of domains, C the set of constraints, when you branch, you are generating a set of constraints. What you have seen in the previous example were two constraints, but you could imagine a multi-way branching. So you have C0, C1, CK. Now, what you want this branching scheme to do is to partition the search space. So that means two properties. The first one is that if you collect the solution to the subproblems, they have to be the same as the solution to the initial problem. What are the subproblems? They are the subproblems which are the same as the initial problem, except that now they have one additional constraint. So you want to make sure that you don't lose any solution when you do the branching. And the second thing that you want to do is that if you have two branches, they don't have to have the same solution. You don't want any redundancy. You want a true partition. And that's what you see here. Every two subproblems don't have any common solutions, right? So that's what a branching scheme has to do. Okay? So once again, branching is generating a set of constraints. Now, what is interesting in MiniCP is that the only thing that you are specifying is a single branching scheme. The same branching scheme is going to be applied at every node. And obviously it's generic, right? So what the branching scheme typically will do is choose a variable, choose a decomposition, and that will produce a set of constraints. And then the depth first search will use these constraints, and I will show you how. Okay? So for instance, if I'm using a static ordering, and at the depth I of my search, I want to branch on variable I and assign the minimum value, or I want to constrain the variable not to take its minimum value. This is the two constraints that I will generate. I will have the branching, on variable I, and it will tell me that xi is equal to the minimum value in its domain, or is not equal to the minimum value of its domain. That's what the branching scheme is going to do. It's going to be completely generic, as I'm going to show you. Okay? Right, so let me show you it. Let me show the branching scheme here in an abstract fashion. Then I will show you the branching scheme for the Queen's problems, and then we're going to see how these things are all fitting together. So this is my very generic depth first search inside MiniCP, but presented in a very abstract way. So once again, I have my constraint satisfaction problem XDC. And the first thing, obviously, that I do is that I apply the filtering algorithm to get reduced domains. If these domains are empty, I have a failure. Therefore, I have no solution. I'm returning an empty set of solution. If all the variables are bound, the size, there is a single, elements in these domains. The cardinality of all these domains is equal to 1. Then I'm returning D star. That's a solution. That's the unique solution that is left. Otherwise, what do? I take my constraint satisfaction problem, but no, with the reduced set of domain, and I apply the branching scheme. When I apply the branching scheme, what do I get? I get a set of constraints here. And then what I do is that I call the search recursively for every one of these subproblems. So from I equals 0 to k minus 1, I call the CP search on the particular subproblems, which I obtain with the same variable, still D star for the reduced domain, but then I have my initial constraint set to which I have added a new constraint. That's the search, okay? And obviously the set of all solution is going to be the union of the solution returned by every one of these subproblems. Beautiful, right? Now, this is the way you can implement that for the Queen's problem, okay? And I'm going to go into all the details so that you understand how to actually do a branching scheme in a constraint programming language, which is implementing using this model plus search paradigm. Okay, so what you're going to see is that this is here in this blue box. This is the branching scheme, and what it's going to do is one of two things. It's either going to say, hey, I'm done. I have a solution, and I'm returning an empty set of branches, or it's going to return two branches. One is going to assign the variable qi to v, and the other branch is going to assign qi. I'm going to say that qi cannot be equal to v. Okay. So let's look at how we do this. So the first thing is to find the variable qi. So what I'm going to do is look at every one of the variable corresponding to every one of the Queen and find the one which is not bound yet, right? So this is what I do. I'm iterating over every one of the variable associated with the Queens, and if the size of the domain is greater than 1, then I'm the index is going to be assigned to that particular Queen. So I find the first Queen, in a sense, in the array, which is not bound, which has a domain whose size is greater than 1. Now, if there is no such thing, if all the variables are bound, then index here is going to be -1. And what I do is that I'm simply returning, hey, I don't need to do any branching anymore because I have a solution. Okay, I'm completing my search here. Otherwise, what do? You have this variable qi now, which is given by the Queen at that particular index. Okay, the variable associated with the Queen at that particular index. I take its minimum value, and now I'm generating two branches. The first one is very, very simple. I'm posting into the constraint programming system the fact that the variable qi is equal to v. Now, you remember what we did in the last video, right? So when you post a new constraint, what's going to happen? You're going to post the constraint, it's going to assign qi to v, and then it's going to propagate. The fixed point algorithm is going to be called, right? And then what are you going to do? The second branches that you see there is simply saying that qi is not equal to v. And what you do is you take these left and these right branches and return them. That's what the branching scheme does. So when you are programming the MiniCP system and you want to define your own branching procedure, what you do is you write this closure which return either an empty set of branching or a collection of branching as an array here. Okay. Now these are closures. When they are executing, they will execute this code here, which will post the constraints or post the constraints or post maybe several constraints. In general, it's a single constraint. All right. Okay. Now I'm ready to show you the depth-first search implementation. So what it does is very, very simple. I'm basically taking my branching scheme and applying the method get. That basically means that I get the branches, and now I have a set of branches that I can execute. If there is no such branches, I have a solution. So I notify the solver, hey, I have a solution. Otherwise, what am I doing? Okay, so what I'm doing here is essentially exploring every one of the branches. Okay, for every one of the branches, what am I going to do? I'm going to call, oops, sorry. I'm going to call the branch that I have. So I'm iterating over every one of the branch. I call the branch, and then I'm called the depth-first search recursively. What happens when I call the depth-first search recursively? I'm at another node, and now I'm basically generating another set of branches. Now the propagation is happening here, obviously. When you call this particular branch, you are posting a new constraint. That's going to propagate the constraints, and therefore, you are calling the fixed point algorithm over there. All right. So that's where these things are fitting together. All right, good. So this is the implementation of the high-level presentation of the depth-first search. You have a solve method which simply calls the DFS. It's also catching exception when you want to terminate the search, if you want to terminate it after one solution or 10 solutions or whatever. Now, what happens in case of a failure? This is one of the things which is sometimes complicated to understand. So look at what is happening here. So I'm basically iterating over every one of the branches. Let's assume that I take the first branch. I call it, but no, I fail. One of the constraints fails, or the domain of the variables is empty and it's calling this exception. I'm going to catch the exception here. And then what is the system going to do? Well, the system is simply going to go and iterate over the next branch because I'm exploring all the branches. So the failure I code by this, exception handler there, and the consequence of that is that you move to the next branch and you explore the next branch. All right? Now, is there a catch? That's funny, right? Because we're catching the exception. But now, is there a catch here in the case of a failure? Think about it. There is one thing which is delicate here. Remember this sparse set? So when we are actually removing the value from the domain of the variable, what is happening? So we are switching, the positions of this particular variable. We are also changing the indices in this particular array, and we are changing the size. Okay. Now, this can be done very efficiently, but one of the things that it does here is that we are modifying the domains in place, right? Now, this is not what my abstract procedure does. Every time I'm applying the filtering algorithm here, I'm generating a new set of domain. That's when I present this thing abstractly. But in practice, we don't do that. No, we basically modify the domain in places. And this is where this particular instruction here, with new state is extremely important. Okay, now let me tell you a little bit what it does. So what we know is that the constraint propagation is modifying the domain in place. So before every branch, we are going to save the state of the system, save the domain, save what needs to be saved. And then we're going to restore it after the branch is completed. Either we had a success, or whether we had, we had a failure. In both cases, we are going to restore the state. So this new state instruction there is actually saving the states and restoring the states. We'll go into the details of this before. Now, what is the state? You know that for these sparse sets, it's the size, maybe the min and the max as well. That's all you need to save, right? And so what you do before you start exploring a branch, you take all these states variable, you create a new state, you put all these guys in, and when you are going to be done with the branch, you are going to restore it, which basically means that you are always using the right nodes, the right domains, the right computational state, the state of the system at the right time. All right. So now you have seen how depth first search is implemented. The only thing that remains to see is how you do this state management. And so the next video is going to talk about this. And once again, you're going to see some amazing thing and some really, really, really pieces of magic there. So stay with us.